Okay, let's continue for the gas solution. Okay? So on Wednesday, or on Monday, on Monday, we derived actually Gibbs energy of the gas phase depending on the pressure, yeah. And so when you have the Gibbs energy, when you have any kind of gas, pure gas component under the different pressure, the Gibbs energy of I, Gi, gas phase equal to Gi naught plus RT ln partial pressure, Pi, yeah. And Pi is of course mole fraction times total pressure of the system, okay. So if the total pressure equal to 1, and if this is the only gas in the system, then Gi, the Gibbs energy of the I gas phase is same as Gi naught, the pure standard gas phase, one component, okay, pure gas phase. So it's okay. But if the total pressure of the system is less than 1 atm or higher than 1 atm, this partial pressure is not anymore 1. So you can have some additional contribution from the partial pressure, okay? And we actually, and after that, we derived the solution, okay, of the gas phase. So when you have the AB gas phase separately, and then if you just allow them to mix it together, we derived actually the Gibbs energy of the gas solution, and compared to the Gibbs energy of gas, the mixture, physical mixture. So it's two separate gas phase. And in the end, we actually found out that the Gibbs energy of the gas solution have lower Gibbs energy than the Gibbs energy of the two physically separate gas phase, okay? And then actually the term, the difference of this gas solution and the physically separate actual gas phase was enthalpy of mixing, okay? So because of the mixing entropy, entropy of mixing, because of the mixing entropy is generated during the mixing of the two gas phase, so we can actually reduce the Gibbs energy. And that actually term is minus T delta S. So delta G of mixing is delta H of mixing minus T delta S of mixing. And if you consider this is ideal gas and without any chemical reaction, then delta H of mixing is 0. And delta S of mixing become minus R XA ln XA plus XB ln XB. Okay? Minus R, yeah. And so you can have that positive entropy of mixing term is generated during the actual mixing of the gas phase. Is it okay? So, in general, the pure material, when you have the solution, it's actually have the more stable than the pure material itself. Okay? So, and also, I just actually try to use the same actually the concept for the even solid phase. So when you have solid phase, there's we cannot actually generate the pure stoichiometric and no impurity phase. There's always certain impurity or there's certain defect because they can actually reduce the Gibbs energy of that material. Okay, so there's always certain equilibrium amount of the vacancy or equilibrium amount of dislocation or equilibrium amount of the impurity. Okay. So we can make a 99.9999% purity, but you cannot have the 100%. Theoretically, it's impossible. Okay? And then I want to actually derive you actually when you have the solution with the gas solution with the reaction. Okay? And then I was keep asking you, okay, whether when you have this kind of the chemical reaction, A plus B become 2C, is it going to be the final actual product is only C gas phase or is it mixture of A, B, C phase? Yeah. Do you recall this one? Let's go back to this one. So this was number 3. So what was that? Chemical reaction. Title was Chemical Equilibrium of the Gas Solution. Yeah. So basically this is this case. So let's assume that in the beginning I have A and the B gas phase. Let's just take this is 1 mole and 1 mole. And then if I make a chemical reaction, and if I mix it together, it will form A, B, C phase. And because A gas phase can react with the B gas phase, and then it can form C gas phase. Let's take this one as 2 moles. Okay? And let's take, when you have this kind of chemical reaction, from the pure Gibbs energy of A, pure Gibbs energy of B, and pure Gibbs energy of C, we can actually derive what's the Gibbs energy of reaction for the pure standard material, between the pure standard material. So when you say delta G naught of reaction, we are not considering that this is the mixture of the solution. It's not solution phase. So when you have the pure A, pure B reacting together and then make pure C phase, then that Gibbs energy difference between this kind of the phase is delta G naught. So delta G naught here means basically 2 moles of Gibbs energy of C phase minus Gibbs energy of A plus Gibbs energy of the B. This is what it means, delta G naught. Okay? So one of your homework is that the handwriting the homework for the barium oxide. So I say you have the barium solid phase reacting with half mole of oxygen gas become barium oxide solid phase. Find out delta G naught of reaction. Delta G naught of reaction, okay? So you have to calculate what's the Gibbs energy of the barium oxide, pure solid phase, and Gibbs energy of barium pure solid or liquid phase, depending on temperature, and then Gibbs energy of oxygen phase, pure oxygen. That will give you delta G of reaction, delta G naught of reaction. Not still means that it's considering everything as a pure stoichiometric phase. Okay? It good? So this kind of value, we can get it always in the thermodynamic table, or you can calculate it from the thermodynamic table. Okay? This is always given. Okay. So, and then let's assume this is less than 0. So this was the question, yeah? So when you have A, B separate phase, gas phase, and then if you actually allow to mix it together, then according to this delta G naught of reaction value, because this is negative, so it means A and B will react together and produce C phase. Because by doing that, by doing so, you can actually reduce Gibbs energy of Gibbs energy by this chemical reaction there. And we believe that that could actually reduce the Gibbs energy of the system. Okay? So the only question is, okay, so when you do it, is A, entire B, 1 mole will react together to produce only 2 moles of C or not. Okay? If this is all solid phase without any solution, then the answer is yes, it will produce 2 moles of C in the end, because that will reduce the Gibbs energy as minimum as possible for the final state. Okay? So equilibrium state, so when this one is in equilibrium state, sorry. So when we say, okay, certain system is equilibrium state, it means that system chemically have lost Gibbs energy. Okay? So it can do the whatever chemical reaction inside, it can make something, it can actually reduce something and then remove something, or I can produce something. But by doing so, if that reduces the Gibbs energy of the system as low as possible, that state could be the equilibrium state. That final lowest energy state, lowest Gibbs energy state, that's the equilibrium state. Okay? So when you have A, B, C, all of them is solid, and then C have the lowest Gibbs energy, and then by making this together to produce C, then only C phase state is the lowest energy state. That's a solid phase. But now when you have the gas phase or solution phase in general, that is not very simple. It is not very simple because we start to have the entropy term in the solution phase. This entropy of mixing is always positive, and then delta Gibbs energy is H minus Ts, so entropy is multiplied with the negative temperature term, so that actually they can make a negative value in the Gibbs energy, okay? So Gibbs energy of solution can be decreased because of the existing of some other phase, actually the component in the solution, okay? So now we have to really compare that, okay? Pure C gas is the lowest energy state, or about 80% of C with 10% of A and 10% of B could be low energy state. Because when you have the ABC together, you can have an entropy term that contributes negatively to the Gibbs energy. Okay, so depending on the case, you may actually have depending on the case, you can have the more A and B to reduce more entropy, because of the entropy, and it can actually reduce the Gibbs energy of solution further, okay? So then, in the many cases, okay, so now we're going to test in this question, okay? So let's assume that initially we have AB phase is mixing, AB phase is entered into the system, okay? So basically, this is my system. I'm adding A gas phase and B gas phase. I inject 2 gas phase, and I know that there's certain chemical reaction like this can happen, because this is thermodynamic table basically. And then I want to know what will be the final gas composition of the system, okay, or final state of the system. Please calculate the amount of the A, B, C, mole fraction of the gas A and B and C. Okay, I mean this is very realistic, very practical actually the question from the industry for the process. Okay, so we have to calculate. There's 2 ways to calculate it. Okay, one of the way is, okay, so from the equilibrium state point of view, okay, it means the Gibbs energy of the system is lowest energy state. Am I right? So if I actually write down actually Gibbs energy of system in the final state, I could say in this way. So one method is like this. So Gibbs energy of system final state can be defined as number of moles of the A phase and Gibbs energy of A phase plus number of moles of the B phase, Gibbs energy of B phase, plus number of C, Gibbs energy of C. And I didn't say this ABC is as a pure phase because it's not, it doesn't have the knot because it's a solution there. Yeah? But this is the partial Gibbs energy of A, depending on the partial, it's a partial pressure. Then we can define partial Gibbs energy times of number of moles of the given actual species, and summation of this one could be the total Gibbs energy of the system. Is it okay? This is okay. And then this can be written again, NA, and then this one is GA naught plus RT ln PA plus NB GB naught RT ln PB plus NC so this is okay. And then what we have to consider here is, okay, so at least we know that PA plus PB plus PC equal to P total. Yeah, that's partial pressure, the concept for the partial pressure. And PI equal to XI P total. So we can consider this one too. And then there's one more constraint. Because we are adding originally A and B phase here, okay, and it produces C, but number of moles of C is twice of the number of moles of the A and B, yeah? Okay? So when you have 1 mole of A reacting with 1 mole of B, it produces 2 moles of C. So when you have 0.1 mole of the A reacting with 0.1 mole of B, it will produce 0.2 moles of C. Yeah? So the Na, Na is the final state, but it means between this Na, Nb, and Nc, there will be certain relationship. Yeah. So Nc will be 1 minus Na plus 1 minus Nb. So any number of moles which actually used for the chemical reaction for the Na and Nb, that will be total number of moles of Nc from this chemical reaction here. Okay, it's a mass balance. Okay, if you assume that there's only 1 mole in the beginning and 1 mole in the beginning, then X moles of the A is reacting with X moles of B, then 2 X moles of C is producing. So 1 minus A, 1 minus B, and then that will be Nc moles. Is it okay? So under this condition, we can actually solve this problem here. And then basically I can change the PA, PB, and PC. Basically I change the mole I for the A, B, C phase. But as I mentioned, C, and then because of the mass balance here, one of them is independent. One of them is dependent, sorry. There's only 2 of them is, or actually in this case, only one of them is independent eventually, because we also have this constraint, 1 actually producing 2 here. Okay, so I'm changing the mole fraction of XA, then automatically XB will be changed and XC will be determined from there. Yeah, do you understand? So by changing the XA, we can numerically calculate when is the minimum Gibbs energy of the total system. Is it okay? So in the end, equilibrium state is, in this case, can be calculated, okay, dg of system divided by dxi, and at constant temperature and constant total pressure, for example, if this is 0, that's actually the equilibrium state. The Gibbs energy will decrease, 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 and increase it again. So depending on, so if I just draw the actual graph like this, so this is Gibbs energy of system, and if I change the mole fraction by xi, it will decrease, 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 and then increase again. So this state. This is the answer we want to get. So this is mole fraction of xi gas phase. So if you just basically, in this case, we can use the xa as actually the variable, and then we can change all these PA, PB, and PC as a function of XA, and then if you put the pure A Gibbs energy, B Gibbs energy, and C Gibbs energy, because we know this delta G naught, so even we can make a relationship between A, B, C, pure Gibbs energy, and then if you just do the derivative of this one, and minimum value, at basically, when the derivative becomes 0, at that condition, what's actually the XA? If I know that one, that would be the actual minimum Gibbs energy condition. So if I know XA, XB, XC can be also calculated automatically. Okay? So this is typically what we are using in the numerical software. Okay? Because we want to make a very general equation. So this is the most generalized kind of the equation we can use it in the big software. Okay, thermodynamic software, we are using this way. So to find out equilibrium state. Okay? But if you have to do it this way, it's a little bit complicated for you. So we want to have the more simple actually the method to calculate this one. That's actually the number 2, the other method. So the other way we can do it is like this. The other way is, okay, so internally in the ABC phase, so we have, I mean this is final state. So this kind of chemical reaction, okay. So we know that A plus B gas phase will produce 2C over the gas phase. Okay? And we know this delta G naught or reaction. Okay? But equilibrium state means, okay, it's a minimum energy state. Of course, that's actually the definition we want to use actually in this method, first method. And the other way is, okay, when the equilibrium state, your reactant Gibbs energy and your final product Gibbs energy should be same. Am I right? That's another way actually we can see the equilibrium state. Is it correct? At the equilibrium state, your reactant Gibbs energy, so let's just my reactant original here, my product here, and this will change the actual chemical, it start chemical reaction, at certain point this will be same. Then there's no further chemical reaction happening. All right? That's actually another way we can see this problem. Okay? Internally, start to make a chemical reaction, and then at certain point, reactant side, product side have same Gibbs energy, then there's no other chemical reaction happening. Because this is more or less, we call it actually dynamically in equilibrium state. So reactant can go to the product, and then product can go to the reactant. It's same level. So that's the equilibrium state. So if you consider this way, so basically in terms of the graph here, so this is Gibbs energy, and this is the process. And in the beginning, this is reactant, and this is product. So this will produce this delta G is negative, so that's why I'm producing this one and this one. And certain point, this Gibbs energy going up, and this Gibbs energy going down, and the same level. So when you have this condition, then between this one, delta G of reaction equal to 0. That's the equilibrium state, basically. Okay? So why is going down, why it is going up? Because I'm producing something, so then material have the more and more moles of the Gibbs energy, so it should increase. And then this should decrease, yeah. Is it okay? So this one, I say, okay, this is delta G of reaction, not delta G naught. So if you actually consider delta G naught, you cannot change this value at all, yeah? Delta G naught is only depending on the temperature, because we are considering pure material reacting together and producing pure material. So there's no difference depending on the process. That value is fixed, always. And the only way we can change delta G naught is changing the temperature. Because Gibbs energy equal to H minus Ts. It's only function of temperature if you assume that the pressure is constant, yeah? So we are not actually talking about delta G naught in this case. Because delta G naught is considering the pure state, pure standard state, ideal case. But we are not talking about ideal case, we are talking about real case now. When you have a real case, there's some kind of chemical reaction, and then it's a solution, then you have partial fraction, etc. This is not counted inside of the delta G naught. Okay? So we are talking about now real value, delta G. Okay? It's like that. So when you talk about, okay, partial Gibbs energy, GI, we are not talking about GI naught, yeah? GI is real value. GI naught is ideal case value. Okay? So when you have this kind of process, we have to talk about, okay, when you have the chemical equilibrium, so at chemical equilibrium, delta G of reaction equal to 0, not delta G naught of reaction equal to 0. Okay? So then how can I actually write down delta G of reaction? Okay? So when you have A, B, C, this kind of chemical reaction, delta G of reaction is basically Gibbs energy of the product minus Gibbs energy reactant, yeah? All the summation of Gibbs energy of the product material and summation of the reactant material. That's the delta G of reaction. Okay? And then when you do this one, then Gibbs energy product, okay, 2 moles of C gas phase. So it means 2 times Gibbs energy of C, partial Gibbs energy of C. It's not standard Gibbs energy. Yeah. At that condition, in this solution, what is Gibbs energy of C? That's partial Gibbs energy of C. Is it okay? Minus Gibbs energy of A plus Gibbs energy of B. This is reactant here. Yeah? Good? It's not anymore pure because it's as a solution. So now if actually rearrange this one, so this will be 2GC minus is it okay? We can write it in this way. And then, okay, good. So let's just take only 2GC naught and only the G naught value, and GA naught and GB naught. So if you do that, basically that will be, so delta G of reaction here is delta G naught of reaction, because delta G naught of reaction is pure Gibbs energy of 2 moles of pure Gibbs energy of this one minus 1 moles of Gibbs energy of this one minus 1 mole of Gibbs energy of this one. Pure state, pure standard state. Okay, so this is 2 moles of Gibbs energy of this one, 1 mole of Gibbs energy of this one, 1 mole of Gibbs energy of this one. So we can sum all of them as this value plus, and then now plus RT, now this one. Ln PC and 2 moles, so 2. Okay? And then this PA and the PB is in minus, so it's PA, PB. Is okay? So now if you actually look at this one, and now let's go back to the equilibrium state, definition of equilibrium state. Delta G of reaction equal to 0. So at equilibrium state, this is very important. Delta G of reaction equal to 0. So this is 0, not this value. Delta G naught of reaction cannot be 0, almost impossible. There's always some value. Okay? Or plus or minus, whatever it is. The delta G of reaction should be 0 at equilibrium state. So this is 0. Then if you do this, okay, this equation eventually delta G naught of reaction equal to minus RT ln this value here. Now you actually see the very famous equation. So delta G naught of reaction equal to minus RT ln equilibrium constant. I think probably you already heard a little bit this equation. That actually came from this one. Okay, so if I just summarize this one again, this is delta G of reaction equal to minus RT ln K, typically equilibrium constant. We do it in this way. And then K, equilibrium constant is, in this case, is PC square, PA, and the PB. And then PC and the PA, it containing partial, actually, this is the partial pressure, so it's mole fraction of C times the total pressure, and mole fraction of A times total pressure, mole fraction of B times total pressure. So total pressure can be even cancelled out each other on the denominator and the numerator. Yeah? And then you can get only mole fraction of C and mole fraction of A, mole fraction of B. And then we still have also the mass balance equation. So PA, XA, XB, and XC have some relationship. So we can find out what is mole fraction of C or A and B by one equation here. So eventually we derive this one, but many cases, many cases, you remember only this one. This is important, but this is less important than actually this equation. This is important equation. Delta G of reaction equal to delta G naught of reaction plus RT equilibrium constant. It may not be equilibrium constant because if it is not equilibrium, when we say this is 0, when delta G of reaction equal to 0, this is equilibrium state, then those values inside here, we call it as equilibrium constant, K equilibrium. Or some people using Q equilibrium, same meaning. Okay? But depending on but if it is not equilibrium state, then you can have different value than 0 for this value. Okay? So let's go a little bit further here. So delta G of reaction equal to okay, so I say, so case 1, at equilibrium state, delta G of reaction equal to 0, so we can actually calculate what is PA, PB, and the PC. Okay? That's one way. And that's the other one. If delta G of reaction equal to higher than 0 or delta G of reaction is lower than 0. I'm not talking about delta G naught, delta G, okay? Delta G instead of delta G naught. As I mentioned, delta G naught you can find in the thermodynamic table, and it cannot be 0 most of the case. 99% it's not 0. It has certain value, positive or negative value. But delta G is really, there's, three cases like this, depending on the condition. My process condition right now, okay? So when you want to calculate the final equilibrium state, we assume this way, and then we can get mole fraction of the different phase. Typically, that's what we want to know, okay, at equilibrium state. But now, if you have this kind of case, okay, so I'm in the middle of the process. I'm in the middle of the process, not the final state. Final state is there, but I'm somewhere here. I'm wondering, I'm going this way, I'm going the other way. Yeah? That's actually this case. Okay? So at the current state, is the my delta Gibbs energy is higher than 0 or lower than 0 give you what's the direction for the chemical reaction now, yeah? So when you have this one, it means I'm going to the reverse reaction, and this one I'm going to the forward reaction. Backward reaction and forward reaction, yeah? So when you have this one, so let's assume in this way, okay. So you know now how many moles of A and B and C is existing in my system now, okay? And I want to know whether this reaction going to the forward reaction or backward reaction. So that means I know this 3 value in the current state, so I can measure actually the amount of this one. And then I want to know whether this chemical reaction going to the forward or backward to reach to the final equilibrium state. Then basically you have to just enter those number and then calculate this one and to get this delta G of reaction. If delta G of reaction is positive, then it means you are going to the reverse reaction. Reverse direction. So it's a backward reaction. Okay? When you actually put all this number, and if the delta G of reaction is negative, it means you are going to the forward reaction. Okay? So this is transient state. Okay? And of course, in many cases, as I told you, we are looking for this one in the book, but in reality, when you go to the real world, we are actually more concerned about this one. Okay? So you have to know that not only this equation, delta G naught of reaction is equal to minus RT ln K, that's one piece of this actually the equation here. This too is very important. You okay? Okay, now let's just generalize all this equation. Because we see how we derived all this actually the equation here, then whatever chemical reaction you have in the gas phase, now you can easily set up equilibrium state, what is delta, the K equilibrium value. So delta G naught equal to minus RT ln K, and that K can be described by the stoichiometric amount of each, the partial pressure value. Okay? So now, let's consider this way. So in general case, so let's assume I have N, so NA of the GA, NA of A phase, gas phase, plus NB moles of the B gas phase, reacting NC moles of C gas phase, plus NT of D gas phase. So let's assume I have, in the inside of my gas phase, I have A, B, C, D, and then if A, B, C, D actually have chemical reaction like this, and if I know this delta G naught of reaction at equilibrium state, and in this condition my delta G of reaction equal to 0, so in the end my delta G naught of reaction equal to minus RT ln equilibrium constant, and equilibrium constant is the product of the product actually value divided by reactant value, but product partial pressure of C gas phase with the NC, power NC, partial pressure of D, power the ND, and then partial pressure of A, NA, partial pressure of the B, NB. Is it okay? I think you can get this one, yeah? You can derive exactly the same way as we did here, and you can get this one eventually. Is it okay? So, this equation is not the magic. It's very simple to actually derive. And now, how about then, when you have the gas and solid phase together? So that means, now let's assume this kind of box. Okay, there's actually the C phase here, and then we have A gas phase, B gas phase interact with this one to produce C solid phase, for example. So how much C solid will produce? How much A gas and B gas will remain in the end? So it's a gas-solid reaction. It's not gas-gas reaction, yeah? So if I just write down this kind of chemical reaction is A gas plus, for example, B gas equal to C. Let's put it this way. Na gas phase A. Oh, sorry. Na and A gas phase. So this is stoichiometry of the chemical reaction. So it's A moles of the A gas phase plus and B moles of the B gas phase will produce and C moles of the C solid phase. Let's assume I know this delta G naught of reaction from the table. How can I get the mole fraction of XA and XB of the gas phase? And then also, how can I get the how many actually NC moles of the solid is forming? Okay? So, same thing. At equilibrium state, delta G of reaction equal to 0. Okay? So if you actually write down delta G of reaction, so one by one. So NC moles of the Gibbs energy of C solid. So C solid Gibbs energy is, product Gibbs energy is NC times Gibbs energy of C solid. It's a partial Gibbs energy. and plus minus Na Ga gas phase plus Nb Gb gas phase. Okay? And because this is solid phase, if the solid phase is solid is also solid solution, then we have to take into account, okay, this is not pure solid, so we have to add some correction term, which is partial Gibbs energy in solid state. And partial Gibbs energy in solid state, so I'll just give it in this way. Partial Gibbs energy of the I in the solid state or liquid state is pure Gibbs energy of I, solid or liquid state, standard value, plus actually RT ln activity of I, solid or liquid. It's defined in this way. It's exactly same format as a liquid gas phase. Pure. So exactly same format. Instead of the partial pressure, we are using the activity. So we'll derive this one later, but anyway, in this case, if this is pure solid, C solid, then there's no partial, because partial is total. Partial is same as total, yeah? So it's pure. So this is actually the pure solid phase in this case. Okay? Then I know this value, and then to only two actual indication is this one. So if you derive this one further, if you actually take this one, delta G of reaction, so if I take this one, delta G of reaction, I'm only taking the pure one, because this is GA naught plus RT ln PA, yeah? And same thing, GB naught RT PA. So I'm taking only pure value. So this will be NC GC naught minus NA GA naught plus NB GB naught plus RT minus RT PA, RT ln PA minus RT ln PB. As I mentioned, at equilibrium state, this value delta G reaction equal to 0, not delta G naught, delta G of reaction is equal to 0. So this term is same as delta G naught of reaction, yeah? This term is delta G naught of reaction between the pure, with each stoichiometric, actually the stoichiometry of the reaction. Okay? So this is delta G naught of reaction. So if I move this, or if I move this one to the other side, this will be equal to minus RT ln 1 of the PA, PB. So again, reactant below and product on top. And product in this case is solid, pure, so it's 1. And Na, sorry. NB. You good? Here too, yeah, sorry. Na minus NB. You good? Sorry about it. Yep. One in this case, because I'm talking about pure solid. Yeah. But in the end, if you really generalize this one, I mean, we haven't learned actual activity, but later we're going to learn. But let's just write it down. What is generalization already? Okay. So when you have A, for example, solid plus B gas phase, so this is Na, Nb, And then this will be, for example, NC of C liquid plus ND of D gas phase. So let's assume whatever chemical reaction like this. And if you know this is delta G of reaction, in the end, at the equilibrium state, delta G naught of this reaction equal to minus RT ln, almost same as before, but this one is now liquid. So it's not partial Gibbs energy, it's not partial pressure, it's actual activity. So activity of the C liquid at NC, and this is partial Gibbs, partial pressure, PD of the ND, and this is A solid, activity of A solid, and A, and partial pressure of the B and D. So, I mean, this general equation for solid, even including solid, liquid, and gas phase, can be derived exactly the same way. We'll learn activity about probably next week or the week after, but at least, I mean, you already know a little bit about activity, so that's why I want to just show you how this activity term going to the actually partial Gibbs energy for the solid and liquid, it's exactly the same format, okay? And then once you assume that, we can actually get even more general equation for the equilibrium condition. And activity is also mole fraction times something, so you can actually have the activity as a function of mole fraction. Okay, so we can get the mole fraction of the solid and liquid phase simultaneously. Yep. When the pure solid and liquid, the activity equal to 1. It's like a partial pressure, 1. So pure solid standard state, pure liquid standard state. It's because that's the pure, yeah? So then activity equal to 1. It's the same partial Gibbs energy, same as standard Gibbs energy. Is it okay? More or less? So for this kind of thing, we're going to do a lot of the, so don't worry about it. I'll show you how to utilize all these kinds of equation in real, actually the real problem. Okay, before that, let's go back to the one more thing. So number 4. So most of the time we actually assume the gas phase is ideal gas because it's very easy, okay? But in reality, the gas, I mean ideal gas law may apply about 95% of the all problem we are dealing with, but on about 5% of the problem, we still have to count a little bit about real gas property instead of ideal gas, okay? So ideal gas. The assumption of the ideal gas is two things. One, the particle of the gas have no volume. So when you actually shrink it to 0 degree Kelvin, volume becomes 0. That's the ideal gas, yeah. Volume is linearly decreasing with the temperature. Yeah. At 273 Kelvin, we have 22 liters, 22.4 liters per mole of the gas. And then when you shrink it, and when you actually decrease temperature, this volume will be linearly decreased, and it becomes 0 at 0 degree Kelvin. That's the ideal gas. So no particle volume or molecule. That's actually one of the conditions for the ideal gas. The other one is between the ideal gas, there's no chemical interaction. Okay, no interaction between the gas phase. this too is basically the ideal assumption behind in the ideal gas. But in reality, we know that gas particle, gas molecule have a small volume, yeah? And considering, the volume of the real gas phase, the particle actual volume is very small. So there's a lot of empty space between the one particle to the other particle, one molecule to the other molecule. So we can still assume that this is almost zero, but in reality, there's some volume, okay? And also, because the particle and particle distance is relatively big, the distance is actually relatively large, so we don't consider interaction because we cannot see it very well. But when you have lower temperature, the volume is shrinking, and also when you have higher pressure, you can actually push it and the gas phase, and then the particle distance becomes smaller and smaller, okay? When your particle distance becomes smaller and smaller, the particles start to realize that, okay, there's another guys next to each other, okay? So it means it feels some interaction, some energy, kind of field from the other actual particle. So no interaction, this assumption cannot be held anymore, okay? And there's actually really certain gas which actually have more interaction than the other gas, okay? So for example, one of the actually famous one is oxygen. Even the oxygen, when you actually get the oxygen cross each other, there's some kind of interaction between the oxygen, okay? And some CO2, it's the same thing, okay? So people measure a little bit about this kind of thing, depending on the pressure and the temperature. And then they make, okay, so some cases, okay, let's don't use the ideal gas. We have to probably use, in some cases, real gas to describe the Gibbs energy over the gas phase more correctly, okay? So in the ideal gas, we know that ideal gas law is working, so PV equal to nRT. This is working in the ideal gas, okay? And in the real gas, this is not working, so we have to add some correction term to hold this kind of relationship, PV equal to nRT. So that is typically P plus, there's many different equations. One of the equations is like this. And this is equation from the van der Waals. TER, no, TER, is it okay? WALLS, van der Waals equation. It's one of the equations. There's so many other equations, but one of the equations actually proposed by van der Waals is this one. So A and B here. Real gas parameter, okay? And then, okay, because of this one, even in the Gibbs energy, we cannot actually use the normal Gibbs energy term. So here we say partial Gibbs energy equal to standard Gibbs energy of the gas phase plus, okay, and then Pi was small fraction of I and then P total. Yeah, this was the partial pressure contribution into the Gibbs energy of the gas phase. And now in this one, we are actually deriving in this way. Gi, okay, instead of the Pi, we're actually using so-called Fi. And F fugacity. Is it C-I-T-Y? S-I-T-Y? Fugacity. C-I-T-Y? Is it correct? Yeah, fugacity. Yep. Sorry, what? 몰라 볼륨? No, it's per mole. I mean, per mole, of course, this is 0. When you have the m moles of a gas phase, so it's PV equal to nRT. So, you can say it's 1, if you like, per mole. Yeah. Same. Yeah. So, this is slight difference. So, in case of the ideal gas law, and most of the time, when actually using the gas phase Gibbs energy, the partial Gibbs energy of gas phase is the pure Gibbs energy, standard Gibbs energy, plus RT ln partial Gibbs energy, PI, partial pressure. And partial pressure is simply mole fraction times P total of the system. Okay? But in this case, in order to actually count a little bit of this interaction between the particles, so we actually, instead of assuming the correction term from the solution as simply just partial pressure, simply mole fraction, we're actually using some different terminology here, and that's actually F. Here we call it as a fugacity. Okay, fugacity could be still function over the mole fraction times something, but there's some correction inside of that. Okay, but 99% fugacity and the partial pressure is almost same. Okay, the only exception when you have the difference between these two is very low temperature, very high pressure. Okay, and most of the material processing, we don't care. The difference is very small. But when you actually go to the high pressure condition at the low temperature, so for example, we have about temperature around 100 degree or below, and then we have couple of the 100 of ATM or thousands of ATM. Then the volume of the actually gas phases become very, very small. So then you can start to actually use the fugacity if you want to make a more correct calculation. But still the difference is only few percent. Okay, but that few percent sometimes is very critical. So people are still talking about fugacity. But at the moment, most of the cases, you can just assume fugacity and the partial pressure is same. Okay? And one of the actually thing, I also prepared in the actually our lecture note is the gas condensation. So water condensation. So when you have the very low temperature, you start to have this kind of interaction. Then the best way is using really fugacity. Okay? You do not? But in our class, we're not going to use fugacity at all in this class. Okay, now let's look at one more last thing here. Actually, I forgot actually to explain this one to you. And so Clausius-Clapeyron. Clapeyron. I call it CC equation, but Clausius-Clapeyron equation. So this is actually important equation for the one component phase diagram. So typically when you have any kind of the phase, so let's assume we have the magnesium phase. Magnesium have solid, liquid, and the gas phase. Okay. So if one actually draw the phase diagram, so it's a P-T diagram. Yeah, it's like this. So typically when you have solid phase, liquid phase, and the gas phase, it will be like this. So I have solid phase, liquid phase, and the gas phase. So at 1 ATM condition, so for example, this is melting temperature. and this is boiling temperature. And then if you just extend this one further here, this will be sublimation temperature. Yeah? So just draw it a little bit better. So solid, liquid, gas phase. So this will be boiling temperature. No. This is melting temperature. And this one is the boiling temperature or evaporation temperature. And then here, if I just extend this one, solid gas boundary, and this one here is sublimation temperature. Yeah? Okay, solid become gas phase directly. Okay, so how can you draw this kind of diagram, solid, liquid, gas boundary? That's actually from Clausius Clapeyron equation. Okay, so this equation is, relatively simple. So we know that one of the Gibbs energy equation is dg equal to vdp minus sdt. Yeah? Okay. So when you have, so basically delta G so when you have change of solid to the liquid Gibbs energy and etc., then you can actually get this kind of equation too. Okay. So let's assume solid to the liquid change. So Gibbs energy of solid and Gibbs energy of liquid should be expressed. Okay. So dg of solid equal to v solid dp minus s solid dt, and dg liquid equal to v liquid dp dp minus s liquid dt, because P and the T is state function, so it's regardless of your, the solid or liquid or gas phase, at the given actually the condition, your temperature and the pressure could be same. Yeah? So at the boundary between solid and liquid, the pressure and temperature should be same. I want to know this line here, basically. Then I want to know what's the Gibbs, I want to know when the solid and the liquid become same Gibbs energy. Okay? So for the solid phase, I have Gibbs energy of solid equal to V solid. So for the so I will have dg solid equal to V solid dp minus s solid dt. You can have this one, yeah? And also same thing, dg, now liquid phase, V liquid dp minus s liquid dt. I could have these two equations. Okay? And at a solid liquid boundary, this Gibbs energy of solid, Gibbs energy of liquid become same. Yeah. So this minus this one will be 0. Yeah. So dg solid minus dg liquid will be 0. Okay. Then this equation will be, so this equation will be V S minus V liquid. So let's just take it liquid to the solid. So liquid to the solid, V liquid minus V solid dp minus S liquid minus S solid dt equal to 0. Okay? So if I write down this one again, dp of dt, so dp of dt, so I just move this one the other side, and then I divide by the dt, then this will be delta S, solid become liquid, to delta V, solid become liquid. So solid become liquid means V liquid minus V solid, and S liquid minus S solid. Okay? And delta S equal to delta H of the T transition. Yeah? Is it okay? So then delta S solid liquid is delta H of solid become liquid and delta V solid become liquid by 1 over T solid liquid transition temperature. Is it okay? So we can get this one thermodynamically. So it's pure solid become pure liquid basically. Enthalpy change. And then this is more or less constant. Yeah. And then delta V solid liquid, the difference solid liquid, this will be also nearly constant. Yeah. And then this will be one of the T actually function. Okay. So if I know this one, basically I can draw this line from dedication there. Okay? You can apply the same thing for the solid plus gas phase and liquid plus gas phase. Okay? And when you have one thing, sorry, when you have solid plus gas phase or liquid to the gas phase, there's two things we can consider. One thing we can consider here is, okay, so this one is solid liquid and this one is liquid solid plus gas phase, liquid plus gas phase. Delta V is solid compared to the gas phase or liquid compared to the gas phase. And this is nearly same as only gas phase. Okay, so you can make approximation then dP over the dt of the solid to the gas phase or liquid to the gas phase is almost like this one delta H of transition, whatever transition it is, and this is only V gas phase, nearly same as V gas phase only, of the 1 over the T transition. Okay? So mainly depending on this delta H. Yeah. So then we can actually get all these different slope. Is it okay? And that's basically the Clausius-Clapeyron equation. Okay? And for you to practice this one, because this was, I'm telling you, this was one of the 6 questions which we gave to the graduate student to do the qualifying exam. Explain Clausius-Clapeyron equation, and then using that, explain why this slope is typically like this. Okay? So basically, this one and these two relationship, that's actually basically slope, yeah? It's not very typical. It's relatively easy. And luckily about 85% of the graduate students get 100%, about 15%, or no, actually, about 50% they got the perfect score. Another 50%, they misread it. They don't know exactly what was the assumption, so they just say, okay, because delta H is big, or delta S is big. No, I mean, that's not enough in some cases. Okay? And you can find this kind of example in anywhere. It's even in the Wikipedia, we can find exactly this equation. Okay? And I'm going to give you this one as a part of the homework number 2 too. So you can really try by yourself. Any question? Any question? So this is the theory part for the gas solution. So at least we now know how to calculate equilibrium when you have only gas phase, or by using this one, we already now calculate when you have the equilibrium with a pure solid or pure liquid with a gas phase. Is it okay? So next week, next week for 2 class, we're going to practice all this one for the real problem. Okay?